So, okay. So complex functions. Complex functions and complex analysis. We'll do complex analysis and then complex functions, then complex differentiation and complex integration. So these are the things that are involved here. Now, let's begin. Okay. Now, first, definition of complex functions. So, just like in real functions, there is mapping between a domain and a codomain. So, as much as there is mapping between domain and a codomain, yeah. Similarly, in complex functions also, there's a mapping between a complex set. This is a set. This is a domain of complex numbers. This is also codomain of complex numbers, and we have Z1, Z2, Z3 as complex numbers, and they result in another set of complex values. Let's say I'll write capital Z1, capital Z2, capital Z3, so on. And there is a relationship between them. How exactly? Depends on what the function is. Okay. So this is a complex function. Now, before we actually enter into the complex functions, we'll discuss some important complex sets. Because we should know how to map from one set to another. So these are complex sets, important complex sets. Now, first one, modulus of Z minus A equal to R. Now, going back to our concept of complex numbers, all right, I'll write here as notes some things that we'll refer to from the basic theory of complex numbers. Now, mod of A minus B is the distance between the complex points. The side notes, I'll say. The distance between the complex points A and B. All right. So remember, a real number requires a straight line to be plotted, but a complex number requires a plane. This is the Argand's plane. Complex number requires an Argand's plane to be plotted. So this is, say, point A, and this is point B in the Argand's plane. So A will have its own coordinates, say x1 plus I y1, and B. So real numbers are plotted on the horizontal axis and imaginary numbers are plotted on the vertical axis, the y-axis. So let's say A is x1 plus I y1 and B is x2 plus I y2. So modulus of A minus B. Okay, we can write this as x1 comma y1 in Cartesian form and x2 comma y2. Now this modulus of this is under root of x1 minus x2 the whole square plus y1 minus y2 the whole square. So modulus of A minus B represents the distance between the 2 points A and B. Okay, this is modulus of A minus B. Now Z is a complex variable. Okay, that means it is not a fixed number, it is a variable, it keeps changing. Now Z changes such that from a fixed point A, its distance is a constant R. So what does this represent? So this is this point A. Okay. So okay. So this is the point A and Z is any point such that its distance from a fixed point A is always equal to R. So this is the definition of a circle. So this Z minus modulus of Z minus A equal to R represents set of all Z, okay, which lie on a circle with center A and radius R. So center at this point A and the radius R. So this is the representation. Modulus of Z minus A equal to R represents this. Okay. Next. So now, what will this represent? Modulus of Z minus A less than R. What will this represent? Anyone? This will represent region within the circle. Correct? This represents all points within the above circle. So this is called as open circular disk. Open circular disk. Okay. Next, what is mod z minus a less than or equal to r mean? Now, this represents all points on and within the circle. So all points on and within the circle. So this is called as the closed circular disk. This is called closed circular disk. Next. Okay. Now, important, this, yeah, we will write the same thing again here. This mod z minus a less than r, or better to say is less than epsilon or delta. Okay, delta is the common term. Okay, where delta is small. Okay, this represents a delta neighborhood of the point A. This will be important for us to define in calculus definitions. So this is a neighborhood. Okay. Now, next. Now, suppose modulus of z minus a lies between R1 and R2. Now, this is going to be like this. Okay. So this is the point A. This distance is the smaller one, R1, and this is R2. Okay. And modulus of z minus a, that means distance of z from A is greater than R1 but less than R2. So z represents all points within this disk. So these are all the points. So it's this region. Okay. So this is called as, you know, this represents an open annulus or open circular ring. Now the same thing, if we write it as modulus of z minus a lies between R1 and R2 and includes R1 and R2. So this represents what? A closed annulus. This is called a closed annulus or a closed circular ring. So the difference between the first and the second is, in the first one, Z would take values only in between these two circles, those points that lie only in between these two circles. But in closed circular ring, Z takes values that are on the circle. So Z can be those points which are lying on the inner circle and the outer circle. Okay. And of course, half planes, it is easy. There is a region. If we want to know the regions now, half planes. Real part of Z, real part of Z is greater than 0. This is right half plane. We know what this is. And then real part of Z is less than 0. You get left half plane. Now, real part of Z, sorry, imaginary part of Z is greater than 0. This is upper half plane. And imaginary part of Z is less than 0. This is the lower half plane. So, we know this, that so this portion, this is real part of Z. Real part of Z is plotted here. Imaginary part of Z is plotted here. So real part of Z greater than 0 represents all points to the right of the imaginary axis. So this is real part of Z greater than 0. The other half will be real part of Z less than 0. This entire region on the left. Similarly, now the upper half, imaginary part greater than 0 is this top portion. I'm not plotting. And imaginary part less than 0 will be the bottom, the last two, the second two, the last two quadrants, you can say, third and fourth quadrant. Okay, so these are, some basic sets that we should know. Sets from the point of view of geometrical consideration. Now, let us go for some important definitions. A point set. Okay. Now, point set is simply collection of finitely many or infinitely many points. So it's a set containing either finite number of points or infinite number of points. Next, open set. Open set. So now, if let's say this is again open set S, the definition is if every point of S has a neighborhood consisting of points belonging to S. That means you cannot have an end. Okay. So example are points interior to circle. It is an open set. First one, example, mod Z minus A less than R. So set of all points, set of R. Okay, I should write like this. S is a set of all Z such that modulus of Z minus A less than R. So how is this an open set? Let's go back to the circle. Any open interval, here we said open circular ring or open circular disk. Now, because it is open, there are, because it's an open, it doesn't take these boundary, points on the circumference of the circle. So it takes some point inside. Now, between 2 points, how many points are there? There are infinite number of points. Okay. So now, let's say this is on the boundary and this is here. Now, there are infinite number of points here. So if you take, you will find at least one neighborhood, one small neighborhood at least, such that all the points within that neighborhood, okay, will belong to the same set S. If it was a boundary, we cannot say like that. If the point lies on the boundary, then when we take a neighborhood, there will be some points within the set S and some points here outside the set S. Whereas if we take a point as close to the circumference as possible, still we will have at least one or many, you can say, you will get a neighborhood which completely belongs to S. So that is what is called as an open set. So open circular disk is an open set, open annulus is an open set. Then we have half planes. Any of the 4 half planes that we discussed, they are all open sets. Okay, these are all open sets. Whenever there is a region is not defined by a boundary, it is called an open set. So this is the geometrical understanding just now what we had. Next, we have what is called as a connected set. Now, this definition is an open set in which any 2 points can be connected. Any 2 points can be connected with a line segment or any path. any line segment or broken line segments which all of whose points belong to S. So let me explain this. So we have taken the example of a circle. We can take the example of a triangle or a rectangular region. Okay. Now I will also take an example like this set of points which belongs to this triangle and yeah, either a triangle. Okay, we'll make two triangles. If not, we could make a circle or whatever it is. Now let's say this is S, this is S, this is S, this is also S, but there is a discontinuity in the areas. One area does not merge seamlessly with the other. Now here, let's say all these consider as an open set. Open set means boundaries are not involved. So now I have, let's say I take 2 points here. These 2 points I can connect with a line segment, or I can connect with multiple line segments. I definitely can connect such that I don't have to go outside of S. Only through all, I traverse 2 points to reach B such that all points are there within S. Okay, all these points, a path from A to B, all belongs to S. Be it a direct path like this or an indirect path like this, they all belong to S. So this is called as a connected set. This is these 3 examples are of connected sets. All these 3 are connected sets. Why? Because they are open sets, and then take any point, I can always draw path. The criteria is that all the points of the path should belong to S. That is called as a connected set. Similarly here. So any 2 points. However, here, if one point belongs to this segment, another point belong here. Now, when we traverse from A to B, we will have to cross a region. I will highlight with red here, this particular region, which does not belong to S. Okay. So these are disconnected or not connected set. Okay. So now let us consider the next important definition of domain. Domain in complex functions. And the simple definition of domain is an open, very important, connected set is called as the domain. So domain is nothing but an open connected set. Okay. Next, other important definitions is complement of a set. Now, set of all points in the Argand's plane except, those belonging to S. So set of all points in Argand's plane or complex plane not belonging to S. Okay. Then other few definitions. Boundary point. What's a boundary point? Whose neighborhood contains both point belonging to set S, and its complement. So neighborhood, so boundary point, just now we discussed, this is a boundary point. Okay. Now what the definition is, let's say this region is S. This is S complement. So what it says is, boundary point is such that its neighborhood, no matter how small, it will contain points within S. Okay. And it will contain points that are outside of S or S complement. Okay. So that is a boundary point. That we understand, we don't have to perfectly define it. Now region. Now region is a set containing or consisting of a domain plus some or all of its boundary points. So sometimes the region can include the boundary points. Sometimes it need not include the boundary points. So what we discussed so far are some important but basic definitions. We discussed some important complex sets. Then we built on defining, what is an open set, what is a connected set, and what is domain, boundary point, and region. So these are basic definitions, but conceptually we have to get it right. We will not dwell on the details of all these. Okay, but from problem point of view, these are all just the basics of complex analysis which we should know. Now, what is a complex function? This is an important definition now. So we have so far, okay, what is a complex function? Now, just like we define a real function, okay. Now, this is a function defined. It is actually a relation, of course. A relation and the function difference we know. I'll not dwell on it. Now this is a function f defined on a domain S function f defined on a domain S now is a relation that assigns, it is a relation that assigns to every number z in S a complex number W. Okay, a complex number W in another set, maybe, or the same set. No, a complex number W. Now this is defined as the complex value W is f of z. Now set of all values of W is called as the range. This we can understand. So now W, which is f of z, will have its components. Now if z is equal to x plus iy, then wf of z will be a function u plus I v, where u is a function of x and y and v is also a function of x and y. Okay, now very important, very important. Usually in real numbers, you remember, if we plotted a function y is equal to f of x, you get a point, you know, which relates a value of x to a corresponding value of y here. Okay, x comma y is the point, and you know, a function defines, you know, whatever the curve may be. All right, so this path defines what is function. Okay, so we are able to plot in real functions, we are able to plot the domain and range in one plane, and we can domain and codomain, you can say, and we can get a relationship within a 2D plane itself. So we are familiar with this one, how to draw graphs of real functions. However, for a complex function, this will be very difficult. Why? Because the domain itself is a plane. The domain itself is a plane. So we call this as the Z plane or the domain plane. Now the domain need not be like infinite. All right, this is x, y. Now z is x plus iy, and z satisfies, let us say, for example, we did this. So let us say that z is an open annulus or open circular disk, or an open circular disk, let us say. So, you know, the domain is set of all points like this. This is the, you know, all infinite points like this. However, codomain or the range is again a completely different plane altogether. It's a different plane. The relationship between the variable and the function value cannot be plotted in the same plane. That is the most important difference. So W is U plus IV, and this is called as the W plane, or the codomain plane, or the functional plane, or the range, whatever you call it. Now let us say it is such that this circle, when it relates to a circle, gets converted to a rectangle, let us say. Okay. Now W takes all values within this region. Okay. So now the mapping is from one plane to another plane. So we cannot plot it as a graph. So that is the important point to remember about complex functions. It plots from one plane to another plane. Okay. So let's move forward. So examples can be taken. W is f of z defined as 1 upon z. So W equal to 1 over z. This is a function, or W, this is z square plus 3z plus 5. This is another function. Okay. Then it need not be just quadratics like that. It can have some complex terms like this. Imaginary part iota multiplied by z plus 6 z bar plus 3I upon z. Okay. So complex functions can be involve just reciprocals, or just polynomial expressions of z, or it can involve z and z bar. What is z bar? If z is x plus iy, z bar is x minus iy. It's a conjugate. So these are examples. Now let us look at the next important concept, is limit of a complex function. I'll not go into the technical definition of limit using the neighborhood and that definition, but limit z tending to z naught f of z is equal to L means, what it means, that it basically means as z approaches z naught, okay, the function value approaches L. Okay, it approaches L. So in this z plane, let's say in the z plane you have this z naught, and here you have L. Okay, now whenever whenever you approach Z0, now you just don't have left hand limit and right hand limit. Just like functions of several variables, we can approach Z0 through any path. Through any path. And whenever that happens, now this Z0, whenever you choose any point which is in the neighborhood of Z0, you will end up with a point in the neighborhood of L, no matter how small it is. That is what is limit means. That means as I approach Z0 in the Z plane, my function value approaches L in the W plane. Okay, the Z plane and the W plane. So then we write limit Z is equal to Z0 of f of Z is equal to L. So that is basic limit. All right. Next, some important complex functions. Yeah. So this is about limits, very simple. We will not dwell so much. We just do on differentiation. We don't go into that level of differential calculus and complex analysis. Wherever we need the important things we do. Although that kind of analysis, as we did for differential calculus, can be there for complex functions. Now, types of functions. First one is, exponential functions. So exponential function. So now we can show that. I will not go into it. I have already shown this in, when we were doing calculus, e power iy, all right, is cos y plus I sin y. So this is an exponential function of, so let us say e power z. So let us say w is f of z, which is x e power z. Now e power z will be what? E power x plus iy, which is e power x times e power iy. Now this is e power x times e power iy will become cos y plus I sin y. So therefore, exponential of z, e power z, becomes e power x cos y plus I times e power x sin y. Okay. So this is u is e power x cos y, and v is e power x sin y. So e power z can be written as some real part plus imaginary part. So this is an exponential function. Okay, this one. So we have built here. So this is an exponential function. Next, circular functions. Now circular functions are, sine and cos. So how can we define them? So sine z is defined as e power iz minus e power minus iz by 2I. You can see this when you do e power iz. Okay, e power iz will be, you can write this as cos z plus I sin z, and e power minus iz will be cos z minus I sin z. So when we subtract the two, cos z cancels, you will get 2I sin z. So from there you will get this. Then similarly, cos z is e power iz plus e power minus iz upon 2. So these are circular functions. And from here, tan z is defined sin z upon cos z. And cot z is defined like that. Cosecant, secant, all are defined that way. This is circular. Next, we have hyperbolic. Now, hyperbolic functions. Now, sine hyperbolic z. Okay. Now, hyperbolic functions was like e power x minus e power minus x by 2, like that. So this is e power z minus e power minus z upon 2. Cos hyperbolic is e power z plus e power minus z upon 2. And then tan hyperbolic z is sine hyperbolic z by cos hyperbolic z. Okay. Now, important relations. Very important ones. So we should know this relation. Sine of iz, sine of iz is I times sine hyperbolic z. Cos of iz is cos hyperbolic z. We can prove this. It is not difficult. Okay. Sine of iz. Sin z we know. Sin z was e power iz minus e power minus iz upon 2I. So we apply this here, e power I times iz minus e power minus I times iz upon 2I. What do we get? We get e power minus z minus e power I square is minus 1, right? So e power plus z by 2I. Now 1 by I is equal to minus I, isn't it? Because I square is equal to minus 1. So I into I is minus 1. So, I will be equal to minus 1 by I, or 1 by I equal to minus I. So with this, what happens is you get a minus sign, minus I e power minus z minus e power z by 2. Take this minus sign inside, you get e power z minus e power minus z by 2, which is the hyperbolic function. Okay, so this whole thing is a proof for this statement. Similarly, we can show this cos of Iz is cos, you don't have the item, so you will get cos hyperbolic z. Now tan of Iz, now tan of Iz is sine of Iz by cos of Iz. And the reverse now. What if it is sine hyperbolic of Iz? It is equal to I sine z. Cos hyperbolic of Iz, of course, will be cos z. And tan hyperbolic Iz will be I tan z. So these are some relationships. Okay, now last of the functions. After this, we'll stop for today. Next, again, we'll meet on Thursday to discuss further the differential part. Exponential over, circular functions over, hyperbolics over, and logarithms. How does log function, how is log function defined? Log z to the base e. So now consider how to define this. So consider e power w, okay, e power w. Now e power w now just see, when we write e power x plus iy, okay, I get e power x into e power iy, and this is cos y plus I sine y. Just look at this trick here, what I'm doing. Now, this cos y from basic trigonometry, 2n pi plus y will be same as cos of 2n pi plus y will be same as cos y, and sine of 2n pi plus y will be sine y. Okay, for it doesn't come for odd multiples of pi. For even multiples of pi, this is valid. So we get e power x into e power iy. So let's say this is e power z. So this is e power I y plus 2n pi. So this becomes e power x into e power iy into e power I 2n pi. So this is e power x plus iy into e power I 2n pi. This is rough calculation. This, so e power iw can be written as, e power w can be written as e power w into e power I 2n pi, because it will not make any difference. E power I 2n pi is in fact equal to 1 cos 2n pi plus I sine 2n pi. This is 1 plus 0i. 1 plus I times iota times 0. So e power w can be written as e power w plus into e power I 2n pi. So This is e power w plus I to n pi. Now let this be equal to z. So e power w is z and e power w into I to n pi will also be z. So now you take log of z to the base e will be equal to, from definition, w plus I to n pi. This is a important point. Generally, for one value of x, you should get one value of y. If you get two values of y, it will not be a function by definition, isn't it? One to many we call not as a function, but here it's an exception. So log z is a multi-valued function. That means it will have many values for one variable z. Okay. Now principal value of log z is w, and general value of log z to the base e is w plus I times 2n pi. Okay. Now there are other forms to represent this logarithm. Now logarithmic functions, log of z to the base e. We can also write z, if we remember, in modulus amplitude form. Z can be written as the amplitude or the modulus, modulus and argument form. So this is the modulus r, and this is the argument of a complex number. Okay, r e power I theta. So z can be replaced as r e power I theta. Okay, this is argument of z is theta. So we get log r, which is the modulus, plus log e power I theta, which is I theta. So we can write this as log mod r plus I times argument of z. So logarithm can also be expressed like this. Okay. So this was the basic foundational building block. Now, next class, we come to the differential part, continuity, differentiability, and what we call as the analytic function. What is differentiable function in real functions? In complex functions, we call it as an analytic function. So that's what we'll start from there. Our main part, this was just the beginning part. From there, the main part begins, where you get questions on this in your gate. All right. So I'll stop here. I'll be sharing this video and these notes with you soon, so that you can refer. Okay. So, and I will be giving a short test series for review. I'll keep all the quizzes open so that from time to time you can review them. Okay. Acha, and I'll stop recording.